Hey guys, so you're going to grade your own pretest today. So let's take a look at number one. The rate at which velocity changes is called, so we learned last chapter that is called acceleration. So that's letter C. So that's worth 1 point if you got it correct. And if you answered it incorrectly, then you would not earn that point. The second question that we learned about previously is about objects that are accelerating. So in order for something to accelerate, we know that the velocity has to change. And we learned last unit that velocity is speed and direction. So we would need either a change of speed or a change of direction in order for an object to accelerate. So our options include a car driving in a circle, so constantly changing direction, but it's at the same speed. But since it's changing direction, it's not accelerating. Option B, we have a car that is on cruise control. Cruise control just means that it sets the speed for you and then it will automatically slow down or speed up the vehicle to whatever speed you set the cruise control app. So if it's at 55 miles per hour, it'll stay there. And it's on a straight road, so it's not changing direction. So we're looking at object B being the one that did not accelerate because it's not changing speed and it's not changing direction. Object C is slowing down, so that is accelerating. Object B is speeding up, that is accelerating. So we would choose object B as our object that is not accelerating. That's also worth 1 point if you got it correct. Question 3. Free-falling objects, which are acted upon by gravity, accelerate at, so we learned last chapter, it's at a very specific rate here on Earth at least, and that rate or that acceleration is 9.8 meters per second squared, or option B. So that's 1 point as well. So this section, these three questions, is out of 3 points. So you're going to write however many points you earned in front of that /3. So if you answered 2 of the 3 correct, you'll write a 2 in front of the slash and the 3. Then we get into some information we haven't yet covered. So let's see how we did. Number 4, which of the following scenarios best describes interacting force pairs? Okay, so what's that? So interacting force pairs is another way of saying for every action, there's an equal and opposite reaction. So this is when if I push on my desk here and I'm sitting in this rolly chair, right? I push on the desk, but the chair pushes back on me and I'm able to roll away. So I push on the desk pushes back on me. That's an example of interacting force pairs. So in our examples that we have here, a push that leads to another push on a different object, right? 2 objects involved. It would be option A. So kicking off of a wall, right? The swimmer kicks on the wall. The harder they push on the wall, the harder the wall pushes back on the swimmer so that they can kick off faster when they make the turn. Okay, so option A for number 4, that's worth 1 point. Number 5, which of the following scenarios best describes the law of inertia? Okay, so inertia says that basically that objects are lazy. They don't want to change their motion. They don't want to accelerate. They don't want to speed up or slow down or change direction. So in that case, we are looking at trying to find an example where our object is either wanting to stay at rest, or if it's moving, it doesn't want to speed up, slow down, or change direction. So out of the choices you were given, your option C would be your choice because if you are sitting in a car and the person driving pushes on the gas pedal, the car starts to move forward, right? And you're in the car, but your body wants to stay where it was. So that's why you kind of get that little bit of pushback when someone pushes on the gas, especially if it's quickly, right? Or if we're riding a roller coaster, like Top Thrill Dragster, and the train takes off, we get pushed back in our seat because our body wants to stay at rest. It wants to stay back where it was. So number 5 is C. You get 1 point for that one. Number 6 is worth 3 points because it's a calculation. So we know where we would need to show our 3 steps of work. And I need to get my drawing tool, which is over here. Guys, I like prepared for this. Okay, great. So this one's up here. And so my drawing tool is here. And I don't know, we'll use green. Okay, so we are calculating acceleration. However, when we have calculated acceleration before, we needed to have the final velocity, the initial velocity, and the time. And this particular problem doesn't give us any of those. So there must be another equation that has acceleration in it that we will use for this one. So in order to determine acceleration, we are going to take the net force, which we could sometimes abbreviate as a capital F with a subscript N for net, or you can even write the word net all in subscripts. And you're going to divide the net force by the mass of the object, and we'll represent mass with an M. So my equation is done. That's the first step of my work. Now I'm going to plug in my net force on the top, 30 newtons, divided by the mass, which is 10 kilograms. And then 30 divided by 10 is 3, of course, and then we have that all-important unit to make sure we get correct. So you could totally just look at your units here and say, oh, newtons over kilograms, or newtons per kilogram. Or, since newtons and kilograms are both what we call those SI units, those official units that we'll see time and time again, we can also use the SI unit for acceleration, which we learned last chapter is meters per second squared. So obviously this one was a toughie. If you happened to say that the answer was 3, for example, that's worth half of a point. Okay, so you get 1 point for having the correct equation. You get 1 point for having the correct work with unit. So if you wrote 30 over 10, give yourself half a point. If you only had newtons over kilograms written down, give yourself half a point for that. But altogether, that's 1 point. And then your answer, again, half a point for having the number 3, half a point for having the correct unit. And your unit could either be newtons per kilogram, or maybe because you knew it was acceleration, you wrote meters per second squared. That's worth half a point. Maybe you had no idea what to do, but you put meters per second squared in your answer. Give yourself half a point. Okay, so let's go back here. All right, so we've done this section. So I've perplexed myself as to why that's 5 points. Newton's laws of motion. Okay, I know why. Okay, so we're gonna hold off on adding up the total for our Newton's laws of motion because there's another question that includes that. My apologies. Okay, moving on to our next section, balanced and unbalanced forces. Which of the following occurs if the net force acting on a moving object is anything but 0? So if the net force is a way of saying the overall force acting on an object. So if I have like 3 newtons acting this way and 3 newtons acting this way, the object that is getting pushed on by 3 newtons on either side would have a net force of 0 because they're acting in opposite directions. And like we learned with vectors in our last chapter, if they're in opposite directions, we subtract them. Okay, so, and then of course, if I have 3 newtons of force on the same side of the box, so both pushing this way, then they would add together and there'd be 6 newtons acting on the box. So if the net force is not 0, what will happen to the object? Okay, and they're saying that it's already a moving object. So maybe our box, right? Our box is already sliding, but now we push the box. What would it do? So the object would accelerate, right? So if the net force is anything but 0, it will accelerate, which we know means it will speed up, slow down, and or change direction. 7A is worth 1 point. Number 8, which of the following occurs when balanced forces act on an object? So balanced forces would be exactly like I described before. 3 newtons in one direction, 3 newtons in the other direction. That's balanced. So if that's happening and it's happening on an object that's already moving, then our object would not accelerate. It would maintain its constant speed. If balanced forces were acting on a resting object, then it would just remain at rest. But since this one's moving, we'll say option C for number 8. That's worth 1 point. And then that one we can total up. So for 7 and 8, please total up. If you didn't get either of them right, 0 out of 2. If you got 1, 1 out of 2. And if you got both, 2 out of 2. Okay, in number 9, I'll go back over here because I need to draw. So we've got this picture, okay? So we've got a block, it's on a tabletop, there's a string attached to it. On the other end of the string, there's what we call the hanging weight or the hanging mass. It's hanging off of the edge of the tabletop. And our string is going through a pulley. So this will turn as, like, if we let go of our hanging mass, and as long as obviously it has more mass than the block, it will move down and our block will move toward the pulley. So in that case, they want us to draw some arrows to represent some forces. The first one they want is the gravitational force. So we know that Earth's gravity always acts downward, right? Or more specifically, toward the center of the Earth. So we're drawing gravity and we're drawing it on the hanging mass. So that would be over here. So I'm going to draw an arrow down. And it also told me to label it. So I'm going to label that with a G. So if your arrow down labeled with a G is by the hanging mass, you can give yourself 1 out of these 4 points. And then the next one is called the normal force. Okay, so the normal force is a force that acts upward and it acts out of a surface. So like on my desk here, right? I've got my calculator, I've got a planner here. The reason that these objects don't just fall through my desk is because there's a normal force that's counteracting the gravity that's pulling it down. So the normal force acting on this block would be acting up, and I'm just going to label that with an N for normal force. So if your normal force was acting up out of the block and really out of the tabletop and it was labeled, give yourself 1 point. Next, I need the frictional force on the hanging mass. So friction is always going to act in the opposite direction of motion. So when you rub your hands together, right, the friction between your hands is what's going to increase the thermal energy and make your hands feel warmer. So every time you do that, right, there's a motion and the friction acts in the opposite direction. So if our hanging mass is moving down, that means our friction will be acting up. So again, near our hanging mass, we have an arrow up. The size of it would be pretty small. Okay, so the friction it's experiencing is from the air that it's traveling through, or its air resistance. So air resistance is an example of a type of friction. There are many types of friction we will be discussing. So arrow up with an F by the hanging mass, give yourself a point. And then finally, we have the tension force. So tension is going to act like in a rope or a cord, and in this case, in a string. Okay, and it's going to act in the direction of whatever's causing the tension. In this case, the pulley is causing tension in this string. If the pulley wasn't there, then there wouldn't be, I mean, there would be tension, but not as much, I suppose. So on the hanging mass so tension force on the hanging mass, so that would be, again, along with our string, it'd be pointing toward the pulley, from the hanging mass toward the pulley, and we could just label that with a T for tension. So 1 point for that if you happen to have that. If you only had one of these, obviously give yourself 1 out of 4. If you had none of them, 0 out of 4. It's a pretest, so hopefully you were doing your best, but obviously it's okay if we're not sure about these quite yet. And then finally, number 10, which I have over here. So this is a kind of a combination of the section that says force diagrams and our Newton's laws of motion. That's why the points haven't quite been added up for those. So first, they want us to determine the net force that's acting on this block, which is kind of impossible because the things that you're supposed to have on there are not there. Okay, so let me pause this and I'll be back. Hey, I'm back. I fixed it. Yay. Okay, so they want us to determine the net force acting on the block. So we already determined net force in this problem. That's not true. We did acceleration. Apologies. Okay, let's try it this way. To determine the net force on this one, we're going to look at all of the arrows acting on the block. So first I see that the amount of force that's coming up out of the table, so the normal force and the amount of force pulling down, or the gravity, those are the same, right? So in that direction, they cancel out, or those are balanced. However, when I look at the applied force, so that's just like the push that was given to our block versus the friction, those are not the same. Since they're in opposite directions, I'm going to subtract them. So I am left with 450 newtons. So we'll say net force equals 450 newtons. I should probably show my work just so I can get full credit here. So I might say something off to the side here of like 294 newtons minus 294 newtons equals 0 newtons, and then 1000 newtons minus 550 newtons equals 450 newtons. So our net force is 450 newtons, and then it says then calculate the acceleration of the block. Well, we learned that new equation today, so we can use it here. So to find acceleration, we can definitely use the old equation if we had that data, but we don't, so we're just gonna use our new one. So net force divided by mass. The net force that we just calculated is 450 newtons. And the mass happens to be conveniently written in the block. It's 30 kilograms. And it's been a long day. Oh, 15 is right. Okay, so 15 is our acceleration. Just like before, you could either use newtons per kilogram, or since it's acceleration and the SI unit for acceleration is meters per second squared, and these are also SI units, you can use meters per second squared. Okay, so how do we total that up? So like it says here, you're going to get 2 points here for a force diagram, so that would be this. Okay, so showing your work, 1 point, having the right answer, 2 points. The other 3 points are going to go in that Newton's laws category because this idea, acceleration is net force divided by mass. That's actually Newton's second law. And we, as normal, would give 1 point for the equation, 1 point or another point for the work, and our third point comes from the answer with the correct unit. So you're going to add 2 points to your force diagrams area for figuring out the net force if you're able to, and 3 points on the Newton's laws area if you're able to figure those out. Okay, so going back to this picture then. Okay, so the total, absolute total for all of these adds up to 19. So you're going to put your score out of 19 at the top there. Thank you for enduring this video, especially because this is like kind of a preview of information to come as well. All right, thank you.